This is lecture 4F, and today we're going to discuss the topic of thermochemistry. Thermochemistry is the study of energy and heat associated with chemical reactions. We know that when a chemical reaction occurs, energy can either be released or absorbed. In a process in which energy is absorbed, we call that an endothermic process. If you have a process in which energy is released, that's called an exothermic process. Numerically speaking, if energy is going to be absorbed during some chemical reaction, we say that the change in energy of the system has increased, and so therefore an endothermic process is always related to, mathematically, a positive value for the change in energy. An exothermic process is releasing energy, so the system is achieving a lower energy state. If it's released energy, we would say the energy change for that is a negative value. Now, energy is stored in chemical bonds. Chemical bonds are actually more stable for electrons than free atoms. Electrons involved in bonding are in a lower potential energy state than electrons in free atoms because they're close to 2 nuclei instead of 1. If we take a pair of hydrogen atoms as an example, in each hydrogen atom, the 1 electron in the hydrogen atoms are located in a quantum state called the 1s orbital. The electron is attracted to 1 nucleus. That attraction causes the atom to be stable, but the electron's only attracting to 1 positive nucleus in each of the 2 atoms. If the atoms approach each other and they bond, the electrons actually change their quantum state from a 1s orbital position into a sigma 1s bonding orbital. In a sigma 1s bonding orbital, the electrons are now in the region of space between the 2 nuclei, so the electrons now get to attract to 2 nuclei instead of 1. Greater attraction means a lower energy state. If we're to show that graphically, on the very right side of this graph, where 2 atoms are very far apart from each other, this is when the electrons are located in the 1s orbitals and are only attracting to 1 nuclei each. If the atoms approach each other, they get close enough and will eventually have the 1s orbitals merge into the sigma 1s bonding orbital, and the 2 electrons will now be located in the region of space between 2 nuclei, double the attraction, so the energy state is lower. So hydrogen atoms are actually more stable when they bond together to form a diatomic molecule. Now, the atoms will not continually get closer together, because if they get too close together, then what you have is the nuclei now starting to repel each other, and the energy state, it becomes very, very high. So when free hydrogen atoms exist naturally, they will actually bond together and they will create a diatomic molecule, because that's the system that has the lowest energy state. This graph would be similar for any pair of atoms that are going to attempt to bond together. The only difference would be whatever the atoms are, that's going to determine how low the bonded atoms' energy are. If we take chlorine atoms instead of hydrogen atoms, chlorine atoms are diatomic naturally found, because the diatomically bonded chlorine is lower in energy state than 2 monoatomic chlorine atoms. But because chlorine atoms are a lot bigger and have more shielding energy levels in them, when they bond, the bonding electrons are blocked from the 2 nuclear charges, so they don't attract quite as much. So a graph for the energy of chlorine atoms at varying distances would show that the diatomic chlorine molecule does not have as low an energy. We would say the bond is not as stable as it would be for a diatomic hydrogen. Similarly, if 2 nitrogen atoms were to bond, the nitrogen atoms bond to form a triple bond, which is significantly stronger than a hydrogen-hydrogen single bond, because the atoms are sharing 3 pairs of electrons, and that causes the nuclei to be more attracted. So when a diatomic nitrogen molecule is formed, we would find the diatomic nitrogen molecule to have an even lower energy than the diatomic hydrogen would. So the stability of the bond really just depends upon the nature of the atoms themselves, the number of nuclear charge, the number of shielding energy levels, and the type of bond they make. Now, if you want to break a chemical bond, we have a name for the amount of energy needed to do that. That's called the bond energy, which I'll abbreviate BE. It's the energy required to break the atoms, or to separate the atoms and break the chemical bond. Graphically, it's reading this graph from left to right. If you have a diatomic molecule and you want to turn the diatomic molecule into a pair of atoms, this is the amount of energy you must apply. So that's called the bond energy. You have to put that amount of energy into the molecule to cause the atoms to be separated and break the bond. And so breaking bonds are an endothermic process, and algebraically speaking, that means that would be a positive energy change. If you go the other way around, if you take two hydrogen atoms and you want to turn them into a diatomic molecule, the energy state of the diatomic molecule is lower, and so the formation of the bond actually releases this amount of energy here, exact same amount, only it's going to be releasing instead. So that's an exothermic process. And so therefore the energy change for any time you form a bond would be a negative value. We're going to use these two relationships here to start making some predictions about chemical reactions, because this is going to be one of the main thrusts of this particular chapter. When a chemical reaction occurs, can we predict how much energy is released or absorbed during that process? And we can do that by knowing the bond energies of all of the bonds in each of the reactants and products in a chemical reaction. So we're going to attempt to show you now how to determine the energy change of a chemical reaction from known bond energies. And we're going to try to find the energy change for the reaction for diatomic hydrogen molecules reacting with a carbon dioxide molecule to form two water molecules and a methane molecule. On the reactant side, we have 4 hydrogen molecules and a carbon dioxide molecule. We can imagine that when this reaction occurs, you have to break those bonds in those reactant molecules in order to allow the atoms to rearrange themselves to form waters and methane molecules. In order to break bonds, you have to absorb energy. So in any chemical reaction, if you're going to try to predict the energy change from bond energies, you need to realize that energy must be absorbed in order to break the reactant bonds. And if you have to absorb the energy to do that, the bond energies for the reactants are going to be used as positive values. Now, if we break all the bonds in the reactant molecules and essentially have lots of individual atoms, those atoms will now recombine to form 2 water molecules and a methane molecule. When bonds are formed, because those are more stable, energy will be released. And so we need to realize that energy is going to be released to form the product bonds. And when energy is released, that type of energy change is considered a negative value. So for us to be able to do this accurately, we have to know exactly what bonds are being broken and exactly what bonds are being formed. So that's going to require us to be able to draw the Lewis structures for each of the reactant and product molecules. A hydrogen molecule has only 2 valence electrons. The 2 atoms share those electrons. So the correct Lewis structure for a diatomic hydrogen would look like this. In this balanced equation, we're actually breaking 4 hydrogen-hydrogen single bonds because there's a coefficient of 4 in front of the diatomic hydrogen. There's actually 4 molecules that are reacting. So if you count those, 1, 2, 3, 4, we're going to have to apply enough energy to break 4 hydrogen-hydrogen single bonds. For the carbon dioxide molecule, the carbon has 4 valence electrons. The oxygens have 6 each. That adds up to 16. So the Lewis structure would have to contain 16 valence electrons. And in order to give octets for all 3 atoms, you would have to have a double bond to the left oxygen and a double bond to the right oxygen. This is the correct Lewis structure for CO2. If you're going to break apart the bonds in this molecule, it's true there's only 1 molecule in the equation, but you're not breaking 1 bond. And you're not breaking 4 bonds. You're breaking 2 bonds. There's a bond to the left oxygen from the carbon and a bond to the right oxygen from the carbon. It just so happens that these bonds are double bonds. So we're going to break 1 double bond here, 1 double bond there. So in counting the bonds that have to be broken, the carbon dioxide molecule requires 2 CO double bonds to be broken. We're going to form the bonds in the product molecules. If I draw the Lewis structure for water, water will have a pair of single bonds between the oxygens and the hydrogens. And because there is a coefficient of 2 in front of the water, we're actually breaking or forming the bonds to create 2 water molecules. So I'm going to draw another one. If you want to count up how many bonds are being formed, it's true 2 water molecules are being formed, but it's not 2 bonds that would have to be formed. You have to form 2 bonds in this molecule, and you have to form 2 bonds in this molecule. So you're forming 4 OH bonds altogether to create a pair of water molecules. Finally, we're creating one methane molecule whose Lewis structure looks like this. And in the one methane molecule, you have to create 1, 2, 3, 4 carbon-hydrogen single bonds. So now that we've sort of analyzed what bonds need to be broken and what need to be formed, we can look up experimental data for the bond energies of each of these different types of covalent bonds. Those are found on handout 8. And if you go to handout 8, you will find a list of the bond energies for many different bonds, and on there will include the energy for a hydrogen-hydrogen single bond, which turns out to be 432 kilojoules per mole. They'll give you the energy for a carbon-oxygen double bond, which is 799 kilojoules per mole, the energy for an oxygen-hydrogen single bond, which is 467 kilojoules per mole, and the carbon-hydrogen single bond, which is 413 kilojoules per mole. So in our Lewis structures on the left side of the page, if we assume that each bond represents a mole of bonds, here we're saying you have to be breaking 1, 2, 3, 4 moles of hydrogen-hydrogen single bonds if we're going to assume this coefficient means 4 moles of hydrogen. So if you want to break 4 moles of hydrogen-hydrogen single bonds, we will multiply 4 moles multiplied by the bond energy of an HH single bond, which is 432 kilojoules per mole. The moles will cancel out. This will be the amount of energy needed to break the 4 moles of hydrogen-hydrogen single bonds. It's a positive number because you have to add energy to break bonds. It's an endothermic process. For the carbon dioxide molecule, there are 2 moles of CO double bonds. To break those, we would have to multiply 2 moles by the bond energy of 799 kilojoules per mole. This will now break all of the bonds in each of our reactant molecules. We're halfway done with the problem. Now we're going to create the product molecules. For the waters, we're creating 4 moles of hydrogen-oxygen single bonds. Once again, it's 2 molecules, but it's not 2 bonds that are being formed. It's 1 mole, 2 mole, 3 mole, 4 moles of bonds have to be formed if you're assuming the 2 in the balanced equation stands for 2 moles of water. So if I multiply 4 moles, multiplied by the bond energy of a HO single bond, which is 467, and if I subtract that, because this is going to be the formation of a bond, which is an exothermic process, energy is released, that has to be a negative number, I will now know how much energy is released when 4 moles of HO bonds are created. Similarly, I'm going to form 4 moles of CH single bonds, so I'm going to subtract 4 moles multiplied by 413 kilojoules per mole, and if I add all this up, this is going to give me the energy change for this chemical reaction. If I assume this is a giant addition problem, like I'm adding 432, 432, 432, 432, then I can treat this in significant figures by writing my answer accurately to the ones place. So this will be 1728 kilojoules. To break apart the carbon dioxide CO double bonds, it would require 1598 kilojoules. When I form my 2 water molecules, I'm going to be releasing 1868 kilojoules. And then when I form my 4 moles of carbon-hydrogen bonds in the methane molecule, I'm going to release 1652 kilojoules. And if you add this up, this is going to give you the entire energy change for this reaction. This comes out 194. The significance of this is the fact that it's a negative number. That means that this reaction's overall process is exothermic. So we would predict energy would be released when this particular chemical reaction occurs, and it would be 194 kilojoules released when 4 moles of hydrogen react with 1 mole of carbon dioxide. If we try another example, we're going to find the energy change for the reaction N2 plus 2H2 yields N2H4. In order to do this, we'll have to look up the bond energies found on handout 8, and there's a whole list of bond energies there. Why don't we see if we can go ahead and draw the Lewis structures, predict what bonds are being broken, what bonds are being formed, and then determine the final answer. If you wanted to pause and try to work this out yourself first, feel free to do so, and then we'll continue with the problem. The Lewis structure for a diatomic nitrogen would show that the 2 nitrogen atoms must be bonded with a triple bond in order to make octets for each atom. The hydrogen molecules, once again, have a single bond between them, so we're forming 2 moles of hydrogen-hydrogen double bond, or hydrogen-hydrogen diatomic molecules, so we have to break a pair of hydrogen-hydrogen single bonds. And then the N2H4 molecule, the Lewis structure for this, would have a single bond between the 2 nitrogens, and then single bonds to the 4 different hydrogens. So by recognizing the Lewis structures of all the reactants and products and realizing we have to break the bonds of the reactants and form the bonds of the products, I'm going to have to break 1 mole of nitrogen-nitrogen triple bonds. In the table, you'll have energies of lots of different nitrogen-nitrogen bonds. You'll just have to pick the one that applies in this particular problem, which is the 941 kilojoules per mole. So to break the bond in the N2 molecule, we're going to add 1 mole multiplied by 941 kilojoules per mole. We have to break 2 moles of hydrogen-hydrogen single bonds, so I'm going to add to that 2 moles multiplied by 432. That's all the reactants. On the product side now, what are we forming to make the N2H4 molecule? We're going to have to create 1 mole of nitrogen-nitrogen single bonds, and we're going to create 1, 2, 3, 4 moles of nitrogen-hydrogen single bonds. And when bonds are created, energy is released. So I'm going to subtract 1 mole multiplied by the energy of a nitrogen-nitrogen single bond, and I'm going to subtract 4 moles multiplied by the energy of a nitrogen-hydrogen single bond. Once again, I'll just treat this as a big addition problem. This is certainly 941. The next one will be just like 432 plus 432 will give me an answer accurate to the ones place of 864. This is now a negative number, so I'm going to subtract 160, and I should have put a bar over the 0 to show that's a significant figure in both cases. In handout 8, there is an addendum. It does say on there that if you do have a 0 in the ones place and there's no decimal point or dot, you should assume that is a significant figure. So these are all accurate to the ones place. And this last one comes out negative 1564. If we add this up, this turns out to be 81 kilojoules, which tells us that when 1 mole of nitrogen reacts with 2 moles of hydrogen, this process will absorb 81 kilojoules worth of energy, making it an endothermic process. So we have a way to theoretically determine the energy change in a chemical reaction. We can also do it experimentally, and if you want to determine experimentally how much heat or energy is released or absorbed in a chemical reaction, we will use a device called a calorimeter. A calorimeter is an insulated vessel that usually contains water. It's used to house a chemical reaction, so we actually add reactants to the water, and we do that in order to determine the amount of heat the reaction absorbs or releases. Calorimeter is an expensive device. It's almost like a thermos, essentially. It actually has an outer container that you see here, and it has an inner metal container as well, in which you pour in the water, you place the reactants in them, and then you have a thermometer recording the temperature change of the water. These are relatively expensive, and not that we don't love you, but we've actually found it just almost as easy to use styrofoam cups as calorimeters, and they're way less expensive. So we sort of make a calorimeter out of 2 or 3 styrofoam cups. And the outer styrofoam cups act as an insulator. The inner styrofoam cup holds the water, and then we add the reactants to that. And with a thermometer, we measure the temperature change. The use of a calorimeter is to try to determine how much heat is transferred away from the reactants or to the reactants to make a reaction occur. Heat is abbreviated in physics by a lowercase q, and it's the energy that transferred causing a temperature change. So if a reaction is exothermic and the reaction is occurring in this styrofoam cup calorimeter, then the reaction is giving off energy to its surroundings, which will be the water in the styrofoam cup. So the water will start to heat up as the energy is transferred to it. Why does the water heat up? Because when the water molecules absorb energy from the reactants in terms of maybe photons of infrared radiation being given off, the molecules absorb the infrared radiation and start to vibrate or roll around faster. And if the molecules are moving more quickly, their temperature goes up. So when you increase the random motion of molecules, you're causing their temperature to increase. And that's what happens when an exothermic reaction is done in a calorimeter. It transfers types of photons of maybe infrared radiation to the water molecules in the calorimeter. They absorb that, and each individual molecule starts moving randomly in a faster pace, causing their temperature to go up. Now, if we look at the inside of a calorimeter and see exactly how this works, you can see this would be two styrofoam cups nested into each other, the outer one acting as an insulator, the inner one then holding the water and the chemical reaction we may put in there. If we add two reactants, let's say A plus B, into the water in the calorimeter, and let's say A and B react to form C and D, and when they do, it's an exothermic process, they release energy. So as the electrons transfer from different orbitals, they actually release photons of electromagnetic radiation. Those photons are absorbed by the water molecules. The water molecules start moving more quickly, their temperature goes up. And we can actually tell that the water temperature gets higher. Now, because the calorimeter traps heat, that means any heat lost by the reaction, any heat given off by the A and B, is going to exactly be equal to the heat that's gained by the water in the calorimeter, and that's why we nest several different styrofoam cups together. They're really good insulators. You can hold hot coffee in styrofoam cups. Heat doesn't get out. So we're trying to set up a situation where all the heat from the reaction is completely absorbed by the water. So because the calorimeter traps heat, the heat lost by the reaction is equal in magnitude, but it's opposite in sign to the heat gained by the water solution. So whatever the heat of the reaction is, if it's an exothermic reaction, it's technically a negative value. Let's make up a number, -50. If the reaction has a heat value of -50, which means it's giving up 50 joules of heat, the solution in that calorimeter must be absorbing 50 kilojoules also. And so if the solution's absorbing 50 kilojoules, its numerical value is +50. So we can't say -50 equals +50. We can say -50 equals a negative of +50. So algebraically, whatever the heat is given off or absorbed by a reaction will always equal the opposite sign of the heat that's absorbed or released by the solution itself. Now we can calculate the heat gained by water. We've done this earlier in the semester. It can be calculated by knowing water's heat capacity. Heat capacity has the units of joules per gram Celsius degree. So if we take the heat capacity of the water in our calorimeter, multiply by the mass of the water, and multiply by the change in temperature of the water, we're going to know the amount of heat the water solution has either gained or lost. So the Q of the water solution is going to be the heat capacity of the water solution, multiplied by the mass of the water solution, and then multiplied by the change in temperature of the water solution. If we can therefore calculate the heat of the water solution, then now we know the heat of the reaction. It's going to be the same number, but opposite in sign, because the Q of the reaction is the negative of the Q of the solution. Now, one more concept about what we're calculating in a calorimeter. A coffee cup calorimeter is not completely sealed. We actually put a lid on it, but the lid doesn't make a perfect seal. Air can escape in and out of it. So that means the surface of the water in the calorimeter is being exposed to atmospheric pressure. And over a short amount of time, atmospheric pressure is fairly constant. So for this reason, coffee cup calorimeters are called constant pressure calorimeters because the reaction is occurring against a constant external pressure. There is a function that's been developed in thermodynamics or in thermochemistry. It's called the change in enthalpy of a process. And this is a thermodynamic property that actually exactly equals the amount of heat given off or absorbed when a process occurs under constant pressure. So a second thing we're also going to be calculating in a coffee cup calorimeter is not only the heat given off or absorbed by the reaction, but something called the change in enthalpy of the reaction, which is abbreviated delta H. And it's a thermodynamic property that is equal to the heat absorbed or released during a chemical reaction, as long as it takes place at constant external pressure. So this isn't going to be really significant to you, except for the fact that when you calculate how much heat is given off or absorbed in a chemical reaction, that can either be called the heat gained or lost by the chemical reaction, or it can be called the change in enthalpy of the chemical reaction. They have the exact same meaning. So therefore, any calculated heat absorbed or released by a chemical reaction in the coffee cup calorimeter, which we would abbreviate Q of the reaction, is also the change in enthalpy of the reaction, which is abbreviated delta H of the reaction. So calorimeters allow you to calculate either enthalpy changes of reactions or Q of reactions. It's just two different terms for the exact same thing we're calculating. So let's try an example. Let's say in a calorimeter, we're going to take 50.0 milliliters of 1.00 molar hydrobromic acid and mix it with 25.0 milliliters of 1.50 molar potassium hydroxide at 25.0 degrees Celsius, and we're doing this in a calorimeter. After mixing solution, the reaction temperature reaches, or the solution's temperature reaches 31.6 degrees Celsius. The solution had a mass of 75.50 grams, and the specific heat capacity of the solution can be taken to be 4.184 joules per gram Celsius degrees, which is the heat capacity of pure water. We're going to see if we can calculate the heat of the reaction. So what's happening in this example is we're taking essentially 75 milliliters of water. It's the 50 milliliters of the HBr solution and the 25 milliliters of the KOH solution. We have 75 milliliters of water essentially in the calorimeter, and the reactants that are dissolved in that water, the HBr and the KOH. And because the temperature is going from 25 degrees up to 31.6, the temperature is going up, that means this reaction must be releasing heat. And that heat is absorbed by the water around it. And if the calorimeter is perfectly sealed, the water is going to absorb every last bit of heat given off by the reaction. So we're going to try to measure the temperature change that the water undergoes, and we can calculate how much heat the water absorbs from water's heat capacity, because the heat that the water solution absorbs will equal the heat capacity times the mass times the change in temperature. So the heat capacity of the water solution is 4.184 joules per gram Celsius degrees. The mass of the solution has to be determined, and they said it was 75.50 grams. And when you do changes in temperature, it's important you always go final temperature minus initial temperature to get the correct sign convention. In this case, 31.6 minus 25.0 gives you a number accurate to the tenths place, and that comes out 6.6 positive value Celsius degrees. So we can calculate how much heat the solution goes by multiplying 4.184 by 75.50 by positive 6.6, and that's going to give us a positive value. Because it's positive, that means the water is absorbing heat, which is what we'd imagine from the picture we just saw. The grams cancel out, the Celsius degrees cancel out, and the answer comes out in joules to two significant figures because of the 6.6 Celsius degree change, as 2,085 joules rounded to 2,100 joules. So if this is how much heat the water solution is absorbed, we will assume that if it's a good calorimeter, all of that heat came from the reaction, and therefore the Q of the reaction, the heat given off or absorbed for the reaction, will just be the negative of this number, which turns out to be negative 2,100. So therefore the reaction between HBr and KOH is an exothermic reaction, giving off 2,100 joules. Now, what does that mean? And that's actually an interesting question. I'll give you one more little bit here. When you've calculated the Q of the reaction, that actually means the enthalpy change as well. So you can say the negative 2,100 joules not only is the heat released for the reaction, but it's also the enthalpy change for the reaction. Okay? So that's negative 2,100 joules also. Same number, same answer for both questions. Okay? Now, back in the 90s, there was a TV show called Seinfeld, and they had one episode where Kramer had bought a chicken. He named it Little Jerry, and it turned out Kramer was actually, or not Kramer, but Little Jerry was actually really good at cockfighting. And there's a little scene that occurred in the episode at one point that I want you to see, and I want to talk about the last couple of lines of this episode. So that was the significant part right at the end. See if you caught that. Hey, guess what? Little Jerry ran from here to Newman in under 30 seconds. Is that good? I don't know. Why isn't that good? Or why doesn't he know? Because we don't know how far it is to Newman's house. So what if he would have said this? Hey, guess what? HBr and KOH release 2,100 joules of heat energy. Is that a lot? What's the answer? I don't know. It all depends how much HBr and how much KOH you reacted. Was it 1 drop of each? Was it 5 gallons of each? So it's like going to a gas station. If you were going to pull up to a gas station and the sign just said $25, you go, what does that mean? I can't tell how much I'm going to pay for gas if the sign is just in dollars. What does the sign need to be in so you know how much you're paying? It has to be in dollars per gallon. So when you give a heat value for a chemical reaction or an enthalpy change for a chemical reaction, if they just tell you the reaction released 2,100 joules, that doesn't tell a chemist anything. They need to know, is it 2,100 joules per mole of reactant, per millimole of reactant? And so delta H's are, when they're determined experimentally, are usually given as final answers as joules per mole of a reactant being used or a product produced in the experiment, so people can have a guide as to how much heat is actually being given off or absorbed. So let's see if we can correct our answer to put it into a useful form so that people understand whether this reaction is releasing a lot of energy or little energy. So I've changed the last sentence. We're going to calculate the heat of the reaction in joules per mole of KBr. And in order to do this, we have to know how many moles of KBr were produced. So we're going to need to write the balanced equation. HBr plus KOH is going to be an exchange reaction. When you switch partners, H goes with OH to make water, and K goes with Br to make the KBr. The stoichiometry of this, the equation is already balanced. We're given numerical data about 2 different reactants. We're told that we have 1 molar HBr, and we've used 50.0 milliliters of it. And we had 1.50 molar KOH, and we were using 25 milliliters of that. And what we're trying to do is we're trying to calculate the denominator of joules per mole of KBr. So we want to calculate how many moles of KBr there are. This is a limiting reactant problem, so I'm going to set this up with initial, change, and final mole table to do that. So I'm going to first calculate my moles of HBr and my moles of KOH. For solution data, you calculate moles by going molarity times volume. So for the HBr, it's 1.00 moles per liter multiplied by 0.0500 liters, and that comes out 0.0500 moles of HBr were actually placed into the calorimeter. Multiplying the molarity times the volume for the KOH, it's 1.50 moles per liter multiplied by 0.0250 liters, and that means we're placing 0.0375 moles of KBr into the calorimeter. So now I'll set up my ICF table. The initial moles of the HBr, 0.0500, the initial moles of the KOH, 0.0375, and the product I'm interested in, the KBr, we don't have any initially. And the whole key in a table like this, and you understanding chemical stoichiometry, is that the reactants and products have to react and be formed in the ratios of the molar coefficients in the balanced equation. These molar coefficients are 1 mole reacts with 1 mole to form 1 mole. So that means one of these has to get reacted away, and it's really simple when it's a 1-to-1 ratio. It would have to be the smaller number being the limiting reactant, because if you subtract that from both of these, you'll actually get a little bit of HBr left over. It'll be a positive answer. So the KOH must be the limiting reactant. It has to react with an equal number of moles of HBr, and it's going to form an equal number of moles of KBr because of the 1-to-1-to-1 ratio. So therefore, we can calculate that after the reaction is ended, we'll have a little bit of HBr left over, no KOH, but this is the number we wanted to know. You're going to wind up having 0.0375 moles of KBr produced. So what we'll do is we'll take the amount of heat given off in this particular calorimetry experiment, which when we use these amounts of reactants and products, we found out we released 2,085 joules. If I divide that by the moles of the KBr that were produced, I now have my answer in joules per mole of KBr, and rounded to 2 significant figures, that comes out negative 56,000 joules per mole of KBr. Now these numbers tend to be on the large side, so usually what we do is instead of providing them as joules per mole of KBr, it's a little bit more convenient to make them kilojoules per mole of KBr. So let's make that one final change. Let's convert this into kilojoules per mole. So if I take my negative 56,000 joules per mole of KBr and do a metric conversion, 1 kilojoule equals 1,000 joules. We wind up getting a heat of a reaction of negative 56 kilojoules per mole of KBr, or an enthalpy change at delta H for the reaction of negative 56 kilojoules per mole of KBr.